Hi, everybody. Welcome to the last lecture for the respiratory system physiology. This lecture is going to cover the control of respiration. So we're going to have to go back into the brain and spinal cord and some of those structures to take a look at how our diaphragm, our respiratory major muscle, is controlled both voluntarily and involuntarily. It's kind of a cool design. So first we're going to take a look at the respiratory centers in the brain. So we have in the medulla, we have two centers called the DRG and the VRG. This stands for dorsal respiratory group and ventral respiratory group. So if you remember back in 232 when we were talking about the brain and the medulla, and we talked about some reflex centers, and we were calling the respiratory rhythmicity centers. You can go back and look back in chapter 14 if you want to review that. But this is what that was talking about. These are rhythmic centers. They have a cycle of activation and relaxation that's going to help cause that diaphragm to contract and then the diaphragm to relax. So we have two boxes here. We're going to go over quiet breathing first, which is the one on the right. And then we'll see what happens when we do forced breathing, like think about exercise would be like an example of forced breathing. All right, so DRG is active during inhalation. During quiet breathing, that's the only one that's active. So the DRG gets activated. So if we're going to kind of do a stepwise process here, so we'll start here. Okay, it's a cycle, but we got to start somewhere. So let's say you're getting ready to do your inhalation, right? We've got to contract our diaphragm. It's a skeletal muscle. So this DRG will become active. That leads to the inspiratory muscles contract, again, primarily the diaphragm when you're talking about quiet breathing. That's going to lead to inspiration. And then when you're done, that's it. It's quiet breathing. You've done your 500 ml tidal volume. Then it gets a signal to be inhibited. So no more action potentials. Maybe IPSPs are coming into those neurons from the DRG that control the diaphragm out the phrenic nerve, right? So putting some of those pieces together. And then when the DRG is inhibited, those inspiratory muscles relax, right? So contraction, relaxation. And so this is what's happening, and then passive expiration occurs. So when we're talking about quiet breathing, this eupnea, just normal respiratory rate quiet breathing, we have an active inhalation and a passive exhalation. And that's due to the relaxed state of your diaphragm goes back up into that dome shape. And that's going to help decrease the volume in the thoracic cavity, increasing pressure, air is forced out. And also you need to remember around the alveoli, every alveoli was wrapped with elastic fibers. So when you inhale, every alveoli fills. And then when you exhale, you're not getting the pull with the diaphragm anymore. And then the elastic fibers kind of want to make every alveoli get smaller. So we have inhalation, activation of the DRG, and then relaxation, inhibition of the DRG, relaxation of our muscles. So that's what's happening during quiet breathing. VRG is not even a part of it. So just active DRG for about 2 seconds, and then exhalation for 3 seconds. So a whole respiratory cycle is about 5 seconds. So that's why we kind of do the average respiratory rate is about 15 breaths per minute, which is about 5 seconds per breath in a 60-second minute. So now if we take a look at forced breathing, like, don't want to do that too much, I'll get lightheaded. Again, let's start with the number 0.1 somewhere. So we're going to do some forced inhalation. So that is going to be our diaphragm. So our DRG is activated, but now we're going to bring in our VRG. Our ventral respiratory group has two parts to it. It has an inspiratory center and an expiratory center. So it can do both. So the VRG has both expiratory and inspiratory inhalation and exhalation functions. So during your forced inhalation, we want the DRG to become active, right? So DRG, and then the inspiratory center of the VRG, right? So we're not only are we using the DRG, which we did in quiet breathing, but now we're using the inspiratory center of the VRG. Okay, so that's going to help us inspire. So that might help to control some of our what's the right word? Accessory, thank you. Accessory muscles to help pull up on our rib cage, right? So our pectoralis minor, serratus anterior, our external intercostals are for inhalation. So those might be triggered by this inspiratory center of the VRG. And since the VRG has both, we have to inhibit the expiratory center. So we got to turn off the exhalation, turn on the inhalation plus the DRG. So your inspiratory muscles contract, your expiratory muscles relax, and inspiration occurs. And this is a forced inhalation. Big breath, as you know, bigger than you would a normal tidal volume. Okay, so that's our forced breathing inhalation. So then when we get the signal that we have to exhale, a forced exhale, much more than your quiet tidal volume. Now we have to turn off the DRG and we have to turn off the inspiratory center of the VRG. We got to turn off the inhalers, and now we can activate our expiratory centers of the VRG, right? So we're inhibiting the inhalation, stimulating the inhalation, and now we get our inspiratory muscles relaxed, our diaphragm is relaxing, our serratus anterior, external intercostals are relaxing. But now in this forced active expiration, we're going to bring in maybe our rectus abdominis, our internal intercostals, that transversus intercostal muscle. So that's going to decrease the volume of our thoracic cavity, increasing pressure, actively forcing air out, and then we get back to that cycle again. So this is control at the medulla, right? So we have medulla and then the pons, because the pons is where we're heading next. So this is our rhythmic center. This is kind of sets the rhythm. So quiet breathing versus forced breathing, right? All right, so now let's take a look at what goes on in the pons. And so here, just so we now have a visual of what we just talked about, this is your DRG and VRG. I'll circle it just so you can kind of get that picture. So there's our DRG, there's our VRG. So those are the things we just got done talking about with sending out this motor command. So if you take a look at the descending tracks here, goes out, goes right to that diaphragm. And then also we have some descending tracks that go to our other muscles. So that is the control of the diaphragm and these accessory muscles via the medullary systems, okay, the medullary centers. So now we're going to take a look at our pons, right? So the pons is right here. So these two centers, and again, if you remember, we talked about these back in the pons in chapter 14 with the brain, the pneumotaxic and the apneustic centers. I think we just named them back then. We didn't really go into what they did. Now, these centers can be a little bit tricky because as you can take a look at their little symbols here, one is stimulatory and one is inhibitory. So then if we want to do some overall kind of net inhibition or stimulation, we're going to have a mix and match of these words. So just try to stick with me, pause and rewind if you need to hear these things again. So let's first take a look at the relationship between these centers. The apneustic, which is the lower of the two, this one right here. The apneustic, if you see, has that red arrow going to the DRG. So the apneustic stimulates the DRG. And if you remember, the DRG was our inspiratory part of quiet breathing and also in active breathing. So if you want to increase your inspiration, increase your depth of your inhalation time frame, you would activate your apneustic center. Okay. So now, I don't like that yellow color. Let's get a new color, maybe green. So then that is the apneustic center. So then just above that, a little bit superior to that, is the pneumotaxic. And if we take a look at the relationship between the pneumotaxic and apneustic, is the pneumotaxic inhibits the apneustic, okay? So if we want to stimulate the DRG, we would want to stimulate the apneustic and inhibit the pneumotaxic because the pneumotaxic inhibits the apneustic. So if you activate the pneumotaxic, that would be inhibiting the apneustic, which would be inhibiting the DRG. See what I said? It's a lot of word jumble. So when you take a look at the ultimate goal of what needs to happen based on your situation, you need to not only look at just what's happening in the medulla with setting the rhythm of your breathing, but how is that kind of regulated by these higher centers. And if you'll also take a look, that pneumotaxic can be regulated by higher centers of the brain, right? So we have our diaphragm is skeletal muscle. Our accessory muscles are skeletal muscles. So we have the ability at some times to consciously override our rhythm, right? Have you ever held your breath before? Like you jump in a pool and you hold your breath. Your higher centers, your cerebral cortex, is communicating to those Pontic centers, which can communicate to your DRG, your medullary centers to stop breathing, and you can hold your breath. But you can't do that forever, because eventually you will run out of oxygen, your higher centers will pass out because of lack of oxygen, and then that inhibition signal will no longer be there. Your rhythm centers will try to kick back up. We can also see our limbic system and hypothalamus is part of these higher centers. So think about emotional responses and how that might affect your breathing pattern. So if you've ever been really excited, or even when you're in grief, right, you have the crying. Sometimes you get to that point, or if you've had kids, they kind of get to that point where their breathing pattern is completely changed, and that could be communication from the limbic system. Those emotional centers in your limbic system and hypothalamus can communicate to your Pontic centers, which affect your medullary centers, which are going to change the pattern of your muscle contractions. All right, so if we have stimulus coming from our higher centers, kind of following that red arrow right here, if those stimulate the pneumotaxic, that's going to lead to a slower output of the DRG, right? Because if we stimulate the pneumotaxic, it's inhibiting the apneustic, which inhibits the DRG. If we have an inhibitory signal from the higher centers, if we inhibit the pneumotaxic, it's no longer inhibiting the apneustic, which in turn stimulates the apneustic, which would stimulate the DRG. So hopefully you're kind of run through that a couple times to get those relationships. If you're still struggling with it, stop by an office hour, Zoom office hour, send me emails. So that's the motor commands out. All right, so how do we control our diaphragm and our accessory muscles? Primarily through, it all kind of funnels through the DRG. We also get some CSF chemoreceptors in here, helping to trigger some of that respiratory rate. We'll see that on the next slide. But I also want to point out to you that we do have sensory information coming in from the periphery. So what all this stuff that I've circled in green, I'll get rid of it so it's not cluttery here. So we also have some sensory information that's coming in from cranial nerves, from chemoreceptors and baroreceptors, right? Chemo is chemical signals, baro is pressure. So some of the chemical signals could be oxygen levels, carbon dioxide levels, pH of the blood. Baroreceptors are blood pressure, right? And we also have stretch receptors that can be both stimulatory and inhibitory. So stretch receptors, how much air is coming into your lungs. You don't want to overinflate your lungs because you could cause physical trauma. You could damage your lung tissue. So if they reach a certain point, they're going to start sending some inhibitory signals to the apneustic, kind of here. And if we inhibit the apneustic, then we inhibit the DRG, and we would start an exhalation cycle there. Okay, so all of these control, the Pontic control, the medullary control, chemoreceptors, baroreceptors, stretch receptors, all of this stuff is kind of culminating in the pons and the medulla to determine the rate and the depth at which you need to breathe to maintain homeostasis. That's the whole goal, right? So maintaining homeostasis. All right, I think I've got that. Okay, so now we can take a look at some of these chemoreceptor reflexes. Yes, so in lecture, I'd only cover one at a time, but in the way that I'm doing this on the PowerPoint, I can't. So we will only cover one at a time. Let's draw a line here. So we'll just talk about the top first. All right, so let's say we have a situation in which our normal PCO2, so we're going to be doing chemoreceptors for carbon dioxide, and I'll talk about why that is here in a second instead of oxygen. So when we have normal PCO2, everything's fine. You're just going along your regular 15 breaths per minute, normal tidal volume, all your respiration volumes are fine. But let's say we have an increase in our PCO2. There's a term for this. It's called hypercapnia. So hyper, a lot. Capnia is a root that has to do with carbon dioxide. So hypercapnia means you have too high of carbon dioxide. That could be because your respiratory rate is too low. It could be because you're rebreathing your exhaled air. It could be because you're in an environment where you can't breathe, like you're underwater, right? And you can't do gas exchange because you inhale water and you don't want to do that. So as you increase your PCO2, that's going to be registered. It will diffuse into your CSF. And we have chemoreceptors in your arteries. We have chemoreceptors in your brain for the CSF. And both of those, so we saw that little side arrow from the last slide going in from chemoreceptors in the brain, and those chemoreceptors in the blood vessels stimulate the DRG, increasing respiratory rate. The faster you increase your respiratory rate, the more CO2 you will blow off. You'll decrease your CO2 and you'll get back to homeostasis. So that's if you have too high of CO2. But you could also have too low of CO2. That could also be a problem. And so this term is what we call hypocapnia. Hypo meaning low, capnia being carbon dioxide. So it's the same kind of pattern: decreased PCO2 in the CSF, decreased PCO2 in the blood. So we have all of our receptors stimulated, reduced stimulation, so inhibiting the DRG, reducing your respiratory rate. You're holding on to more of that CO2. That extra CO2 then goes into your blood, bringing up your levels, getting you back to homeostasis. So we have built-in mechanisms that look at or can monitor your carbon dioxide levels. Now you might be thinking, well, why not oxygen? How come we're not having chemoreceptor reflexes for oxygen? We do, but if you remember looking at the oxygen saturation curve, we don't really go too far away from, we only kind of fluctuate between 75 and 97% saturation on our hemoglobin. And so that's a pretty big difference, and our body is okay with that. For CO2, I want to say we have increasing respiratory rate for as little as like a 2 to 5% change in carbon dioxide levels. So our chemoreceptors are way more sensitive to carbon dioxide than they are to oxygen. So our respiratory drive is more focused on carbon dioxide buildup or lack thereof than it is oxygen. So we are in a carbon dioxide drive. And one of the reasons why is because of that carbonic acid bicarbonate buffer equation that we saw back in gas transport, is because CO2, when you have an increase in CO2, it drives that equation to the right, giving off a whole bunch of hydrogen ions, which leads to acidosis, which is a really bad situation. Or if you don't have enough CO2, it drives the equation to the left, and you're tying up hydrogen ions and you become alkaline. So changing in carbon dioxide levels is a big deal. It really can affect wide-ranging systems, primarily due to that pH change. So we are more sensitive to carbon dioxide changes, and we have these built-in reflexes that are going to help with that. Okay, and then just some last little bit here that's in the notes. The last section talks about voluntary control of respiration. So again, we can hold our breath. You have voluntary control when you're speaking. You have to regulate the amount of air that's coming through your larynx, vibrating your vocal cords to give you voice. Emotional states can affect the respiration due to the limbic system and hypothalamic coming down, and anticipation of strenuous exercise can increase your respiratory rate, kind of priming things to get ready for that physical activity. And then lastly, your conscious control has a limit. So yes, you can hold your breath, but eventually your upper centers are going to say, hey, this is stupid. I'm going to take your conscious control away from you. You'll pass out, and then they'll just kick back in doing their rhythmic breathing. So I have there in the notes, you cannot hold your breath till death. And I've heard, luckily this was not my personal experience, but kids who are kind of wanting their own way and they hold their breath and their parents are like, no, I'll give you candy or I'll give you what you want. Just breathe again. I'm not saying this is a parenting tactic, but they'll just pass out and then they'll start breathing again. No, just joking. Hopefully none of you have to deal with that. But all right, so that's the last bit of the lectures that I want to share with you on the physiology of the respiratory system. So hopefully you're doing well with this body system. I know there's a lot of anatomy, there's lots of different moving parts and pieces. So if you are unsure about anything, watch the videos, watch the supplemental things, send emails, come to office hour. I am more than happy to help. All right, so I will see you next time. Bye.